Congratulations on completing week 1 of Foundations of Algorithms. In the first week, we met your tutors and your teaching staff, Janjong and I. Then we went on to discuss why algorithms and the Enigma machine that gave us motivation for developing an algorithm to find repeated sequences of letters in a string. We looked at a number of different methods for doing so, and then proceeded with an analysis of each of these methods, stepping through the algorithm step by step. We looked at big O notation and did an elementary proof of the runtime. Worst case and best case analysis, followed by our very first data structure, a suffix array. We then learnt about a shell, compiled our first program, Hello World, and we're done for the week.
Okay, welcome everyone back to Foundations of Algorithms. Lovely to see you, and I hope you had a great weekend and Monday. One thing we're going to be doing every week from now on is we're going to start off the class with an important historical figure from the history of computing. And one thing that's, I think, particularly important is to make sure that we have a diverse array of people represented in our stories as actually appeared in the history. So this figure is has anyone seen this woman before who has a guess of who she might be? This is Augusta Ada King, Countess of Lovelace, or also known just shortly as Ada Lovelace. She was a close friend of another one of the pioneers of computing, Charles Babbage, and together they designed the first computer, and Ada in particular is renowned for creating the first computer program and the first algorithm. There is a little bit of a dispute around whether it was her or Charles that actually created the very first computer program, but nonetheless she is a really important figure in the history of computing. More than that, because of her impact on the history of early computing in the mid-1800s, we've actually named a programming language after her, the programming language Ada. And over the weekend, I was watching a movie called After Yang. How many of you have seen that movie? Anyone? It was out like 2 years ago, about the future where there's a sophisticated AI. And in that movie, this is the main release, highly recommended. It was fun, go see it. The android's name is actually named Ada after Ada Lovelace. So taking us back to where we were before at the end of last week, and we'll get to the homework problem in a minute, we had this notion of modular arithmetic that happens in C where we've only got so much space for our numbers, and so when we get to the end of the numbers, we start to wrap around again. So we also had this question about what is the biggest number that C can represent, and as my little cousin can tell you, she's very curious to get the answer to the question, which we will get more into today. So what is the biggest number there is? And partially for this question, in this class, we're going to ask the question, what is the biggest number that any computer can handle? Not just your laptops, not just a 64-bit, what is the biggest number that any computer can manage? So then we talked about our way of representing numbers that are larger than what can be stored in the word size of a computer. So if our word size was 2 to the 32, a single one of these clocks could get up to 2 to the 32 minus 1, but we might use a bunch of different clocks to give us more bits in our overall number that we're representing. We asked if C was smart enough to deal with this, which finally took us to where we ended off the class, was our demo. So let's put it up on screen again. We had the biggest number that we could represent positively, which was 2 to the 31 minus 1 in this case. We added 1 to it, we multiplied it by 2, and we also multiplied the biggest number plus 1 by 2, and we got that output. Now, one thing that's different is these integers actually have negative numbers. And so what I'm looking for is someone who can have a guess maybe at what's going on here. Why, when we add plus 1 to the biggest number, do we get negative the biggest number? Why, when we multiply this by 2, do we get negative 2? And why, when we multiply that by 2, do we get 0? So I'll take any answers for a stab at it. You've answered a bunch, so I'm going to leave it to someone else for a minute. You don't yeah, what was your name? Bronson, okay, what's going on? Why am I getting these weird results?
This is not a sophisticated answer, but I feel like it's something to do with how it's reading the, I guess, bits. So, I don't know, adding 1 changes how the bits are arranged, and it can't read all of them, I guess.
That sounds pretty good. So I'm going to put up a picture, and maybe you will help me talk through it a little. And then we'll come back to what you were saying just then, see if we can add a little more sophistication to it. So Bronson, your question essentially gets to the heart of like, how do we represent negative numbers if we've only got so many bits? And you said the computer might try and represent it in some kind of clever way. So one way of representing it might be like this, what we call sign magnitude representation, where let's say we have 32 bits. Let's use the very last bit to tell us if a number is negative or not. So we get all the way to halfway down the clock. Let's give us half the room for the positive numbers, half the way for the negative numbers. And once we've gotten halfway down, which would be, we have 32 bits, 31 of those bits we're going to use to represent how big the number is, and the 32nd bit we're going to use to represent whether it's positive or negative. So this gives us a picture that looks something like this. This is just a kind of a sketch representation. Obviously, the numbers aren't quite perfectly arranged like this. But so if we set our first bit to 1, we get 1. If we set just the second bit to 1, we get 2, 4, 8. And then when we go halfway down, we look at where 0 was. 0 was a single 0, was a string of 32 0 bits. But if we now take the 32nd bit that we're using to represent whether it's positive or negative and flip that, well, that just makes the same number we have negative, and so we get negative 0. So there's something a little weird about this way of representing it, that we have 2 zeros. Then if we move forward from there and we do a 1 followed by 30 zeros and then a 1, we get our negative 1. So that's just like the one we had up there, only there's the 32nd bit is set to 1. OK, so now let's take the number 2. The number 2 looks like 1, 0. But let's also set the 32nd bit to 1, and that'll give us negative 2. So this is one way of doing it. But it still doesn't really explain what was going on with our system in C. This doesn't seem right, because if we take the largest positive number and I add 1 to it, what would I get? Just shout it out. The largest positive number is right over here. If I add 1 to it, negative 0. And what did we get in our test program? I added 1 to big, and what did I get? I got the negative version of it. So it doesn't seem like the computer is representing things using sign magnitude representation. So what are some problems with sign magnitude representation? Why might we choose to do something different? What was your name? Michael, and you've already answered a question for me before at some point. OK, go ahead.
Well, if you want to do something like 1 minus 2 in arithmetic, sign magnitude wouldn't really work, because when you do that, then you get the lowest negative number instead of just getting to -1. So if you flip it around, so that when, I guess, the wraparound goes to get the lowest negative number, you can actually do arithmetic like 5 minus 6. Actually work instead of freaking out and outputting the lowest negative number.
So Michael is totally right. The way he said it is possibly going to be a little complicated for all of you to understand right yet, so we'll get to it. But he's making the point that it's actually kind of tricky to figure out how arithmetic works this way, because if you take, say, 8 and negative 8 and try to add them together, and try and do that using the bits, you're going to get results that you don't expect. It's not going to work to simply rearrange the bits and add them together. So we need some other mechanism that allows us to use the bit form, because this is what the computer actually stores, to make arithmetic easy. What about another problem? There's something weird about this clock. Yijin. There are 2 zeros. A bunch of you pointed this out. 2 zeros obviously makes for a kind of a strange number system, which is also going to give us problems when we try to do arithmetic. So we switch to something that looks more like this, 2's complement representation. Now Bronson, if we take the largest number that we can represent and we add 1 to it, and we're using this representation, so Bronson, where's the largest number? Where's the largest positive number?
1,000.
It's this one down over here. And then what happens if we add 1 to it?
Then the sign is flipped, is that right?
So this isn't sign magnitude representation. Sign magnitude representation was where we took the 32nd bit and we flipped it. But look at the arrangement of this clock. If I go from 0, negative 1 is on that side, then negative 2, then negative 3, then negative 4, etc. once we add the relevant bits. What happens when we get back down to here? Are the numbers increasing or decreasing as we go down the clock? In magnitude. Yeah, they're increasing in magnitude. So we start, if we're looking at the positive numbers and we go clockwise around the clock, we get bigger and bigger and bigger. If we do the same with the negative numbers, the number gets bigger and bigger in magnitude, although it's getting more and more negative. And so by the time we get down to the bottom, we will have the smallest or the biggest negative number in terms of magnitude. I have to be careful with that. Yeah, we'll have the negative number that's biggest in magnitude. So that means the actual digits should be very, very high. Let's see what we got from our program. We got all the way to the biggest number, and then we went one more space over in the clock, and we got the negative number that had the biggest numbers. And because we've split the clock evenly between the positive and the negative numbers, you go directly from the largest positive number to the largest negative number. So now what happens if I multiply this by 2? Where's that going to take me? Yeah, what was your name? Kai. So if I multiply the exact 6 o'clock position by 2, I'll get to 0. What if I'm one place away from the 6 o'clock position? So if I'm 6 o'clock minus 1, would I get minus 1 or minus 2? So if I am 1 away from the exact halfway point, which I am in this case, I'm 1 away from the halfway point, and I multiply this by 2, I'll be 2 steps away from getting the full way round. And if I get the full way round, what number do I get? 0. And so what's 2 steps, let me go back to this. What's 2 steps away from 0 in the negative direction? Negative 2. So if I look at my output, negative 2, I'm 2 steps away. Now what if I'm exactly on the halfway point? If I'm exactly on the halfway point, Kai said it a second ago, what do I get back to? 0. So that tells us that this is exactly on the halfway point, and I'm getting back to 0. So this is called 2's complement representation. And the reason why it's called 2's complement is because of the way that the bits are actually represented. And we'll do a demo of that on the iPad in just a second. So the way that we switch a positive number into a negative number is by this simple algorithm. So take the positive number, flip all of the bits, and then add 1 to the number doing a carry. And we'll talk about the carry on the iPad in just a second. Okay, so let's start with representing the number 8 in binary. So this is one way of writing it out and one way of converting it. And in the exercises and workshops, potentially next week, we're going to get you to do some of these conversions yourself. So here's the number 8 in binary. It is equivalent to 0 because it's, let's start at the other end. I've already noticed a giant mistake on this. Should be 0 plus 0. So there's an 8th place in the number 8. And so I would write that 1, 0, 0, 0. So there's a 0 in the 1's column, a 0 in the 2's column, a 0 in the 4's column, and a 1 in the 8's column. Make sense so far? Yep. Okay, so let's follow our algorithm to convert it to 2's complement. So what was the first step? Anyone remember? It was just on the slide. Flip all the bits. Okay, so let's flip all the bits. 0, 1, 1, 1. And now let's add 1 to this number. Okay, so I'm going to add now who notices what I've done here? I've added another bit. The reason I've done this is because if I took what we had before and I added 1 to it, well, 1 plus 1 is 2, but we don't have 2, so we put an extra 0 in this column, and then we'd carry the 1 onto the next column, just like grade school arithmetic. 1 plus 1 is 2, but we only have 1s and 0s, so we put a 0 there. 1 plus 1 is 2, okay, and then we add a 1, but that doesn't work because that gives us the same number as we initially had represented. So what this tells me is we actually didn't have enough bits to represent the number that we wanted. We're going to need another bit so that our number system works. So let's reverse all this again. And now I'm going to go back. And I'm going to add ourselves another place. So now this is the number 8, except now we've represented the number 8 using 5 bits. And really, on our computer, we've got many more bits here. But let's imagine we're using a 5-bit system for the time being. OK, step 1, flip all the bits. OK, 1, 0, 1, 1, 1. Now what do? Add 1. So it's plus, and let's, yeah. Oop. OK, so 0 plus 1 is, oh, add 1 to this. Ah, I've screwed this up. We're just adding 0, 0, 0, 0, 1. We're adding these numbers together. So 1 plus 1 is 2, but we don't have a 2, so what do? Carry the 1. 1 plus, come on, say it, is, OK, I put a 0 there, what do? Carry the 1. Carry the 1. And now I've got a 1 there. And now 1 plus 0 is 1. And I have negative 8. And so in this way, the number negative 8 is kind of just a modified mirror of the positive number 8. So we flip all the bits and add 1, and that's how we do it. OK, one more example for all of you to do on your own now. And I'll give you a minute or two to convert this number 9. So the first step, you have to write it out in binary. So it's an odd number, so think about what that means. Figure out how many bits you need. And then we'll do it on the board really quick once all of you have worked it out. OK, so first thing we need to do is convert the number 9 to binary. So even without having a very solid algorithm, you can think of this as the number 8 plus a 1 in the ones column. So this is a 1 in the ones column, a 0 in the twos column, a 0 in the fours column, a 1 in the eights column, and then we remember how we needed that extra digit, so we have a 0 in the last one. So that gives us, if we're reading it off in the right direction, a 0 in the 16s column, a 1 in the 8s column, a 0 in the 4s column, a 0 in the 2s column, and a 0 in the 1s column. And if we figure that out, 1 plus 0 plus 0 plus 8 is 9. OK, now what do? I flip the bits. So that gives me a 1. Let's see if I can do this. This pointer. There we go, laser pointer. So we flip the 0 to a 1. The 1 becomes a 0. The 0 becomes a 1. The 0 becomes a 1. The 1 becomes a 0. And then we add 1. 0 plus 1 is 1. And so there's no carry. So we get our final result here. So in your workshops, you're going to have a number of these exercises where you actually learn how to convert algorithmically a number from decimal to a binary representation. Maybe that'll might wait a week or two, but you will get that. And you will also have exercises of how to manipulate numbers from positive to negative, as well as getting a handle on how the arithmetic actually works in a more visceral sense. Because I can show you this all day, but until you actually start practicing with it, we're not going to get very far. So that should roughly conclude our discussion on negative numbers. But there's still, a little more to come. Just like we did with positive numbers, if you want to represent larger and larger negative numbers than are available using the width of the word that is in your computer, you can always add a few of them together. Now again, we're not expecting you to do this manually. It's actually quite a lot of work to manipulate the bits so this works. The easiest way to do it is to include a library, but you're not going to have to deal with these super large numbers in the class. So this is more for your enrichment. OK, we did that. And as Admiral Akbar says, it's a trap. So if you're having trouble with your numbers in your computer, if you're finding that you're getting weird arithmetic results, quite possibly what is happening is you're running into an integer overflow or underflow error. And this is what we call when you go over the maximum size of your integer and you start wrapping around either into the negative numbers or into the positive numbers, depending what's happening. So we've now learned about a whole lot of types. And one thing that's useful to know is that not only do we have the integer type, but we also have the long type, which is like an integer that has more bits available to it. And so in this way, even if our computer is only 32 bits by default, C does include some ability to represent larger numbers, so it might be 64-bit. However, the C specification does not always promise you that a long is strictly bigger than an integer. So even if it is the case on most 32-bit computers that a long is 64, it's up to the compiler that you've downloaded. The compiler could make both an int 32-bit and a long 32-bit. So the type system only gives you this order of guarantees. At the very bottom end, we have a character, which is ordinarily 1 byte. But again, the only guarantee you get from the compiler is that it's smaller than or equal to a short, which is smaller than or equal to an int, which is smaller than or equal to a long. You might encounter shorts 1 or 2 places in the class. It's a kind of an intermediate value that can fit between an integer and a character. So in many cases, it's going to be 2 or 4 bytes, depending on the computer you're on. There are also minimum sizes that the C specification sets. For a character, it has to have at least 256 values. A short has to be at least 2 to the 16. An int has to be at least 2 to the 16. And a long has to be at least 2 to the 32. But again, as we've said, most of our devices are now have a 64-bit word size. And so an int is typically going to be 2 to the 64 now, and a long, I think, is typically 2 to the 128. No, 2 to the 96? 2 to the 64, OK, I'm wrong on this one. The best way to actually figure this out is to run, we've got a sample program in the workshops that you can run on your own computer and figure out what each of these types is actually giving you. For the most part, you're not going to have to think about it, but it's really important to know for when things go wrong. The other kind of trap that we can run into here is floating point precision. So we've already seen decimal numbers in the class so far, but how much memory does your laptop have? Let's talk about RAM. So this is the temporary working memory of your computer. So just for one of your laptops, who knows how much RAM their computer has? Doesn't matter if you're wrong. Ahmed? 32 gigabytes, someone else? That's a nice laptop you've got.
8 gig.
8 gig? 16? OK, so it's a finite amount of memory. Now, with a finite amount of memory, we're not going to be able to represent a number that has an infinite number of decimal places. If we've got too many decimal places in our number, our computer is going to have to start making choices about which decimal places are actually important. In C, there are 2 types that we're going to encounter right now. They're the float, which for the purposes of this class, you really shouldn't use. I've mentioned that before, and a double. And what a double is it's actually saved twice the number of space for numbers after the decimal point, or for numbers with a decimal point than a float has. So how many decimal places can a computer represent a random real number? So if I pick a number from the reals, how many decimal places does it have if I pick a random number? Do real numbers have a fixed number of decimal places? No. OK, so why does the number 0.3 not have a finite number of decimal places? What was your name? You'll have to say it a bit louder than that. Muhan. OK, so the number 0.3, how many decimal places, how many numbers after the decimal place does that have? Yeah, when we say 0.3, what we're actually covering up is that there are zeros after the 0.3, and those zeros are actually important. Because if we were really picking a number from the reals, numbers from the reals can have infinite numbers after the decimal point. And if we do pick a random run, there are not infinitely more. There are an uncountably infinite number of numbers that have decimal places where at least one of the decimal places after any finite count is set to something positive. So let me word that in another way. So let's say I pick a number that has a random number of decimal places, where a positive value. So let's say our number has 67 values after the decimal place. there are infinitely more numbers that you can come up with that have things more than 67 places, that have numbers in more than 67 places. So it turns out if we're going to really pick a random number from the reals, there is a really, really, really high probability that we're going to pick a number that has positive values in the infinite decimal places. So even our idea of like, let's just throw out all the ones that are zeros doesn't really work. There are too many numbers out there, and too many of them have numbers after the decimal places. So I won't expect you for the exam to be able to represent that argument either formally or even informally. It's more a kind of a taster for our problem. Because not only is the number of decimal places that we can represent in our computer with 8 GB of RAM limited, it turns out that the number of decimal places that one can fit in the entire universe is limited too. There are a bunch of research papers that actually talk about this. What are the fundamental limits of computation in the universe? So why did I show a black hole? It was Young that was studying physics? Yes? Why did I show a black hole when I was talking about the number of numbers that we can fit in the universe? No? Okay, behind you. What was your name again? Victor. Because it's cool? Yeah, that's a good answer. Anyone else? This is a physics answer to what seems like a computer science question. Why did I show a black hole? Kind of, but not really. So let's say that we have a computer of a given size, and I want to start packing more bits into it. So I make the computer's memory more and more dense. And let's say that I'm being very generous, and I make the computer larger and larger and larger. If I make the computer larger and larger and larger, what's going to happen eventually? If I make the computer contain, like, what will happen? Can I keep doing this forever? Can I keep making a larger and larger computer? Well, so one problem that we're going to run into is we have the speed of light limit. So eventually I'm going to have created a computer such that the signal from one end of the computer will never reach the other end of the computer by the death of the universe. So that's one problem with creating a computer. Now what about the other direction? What if I try and fit more and more bits into a smaller and smaller device? Let's say I pack the atoms closer and closer together, and I use each one of the atoms to represent another bit in the number in some way. Yeah, so eventually I will have made my memory packing so dense that I will create a black hole. So it turns out there is actually a fundamental limit to the size of the computer you can make that is bounded by the speed of light, the amount of space that's actually available in the universe, and how densely we can pack matter in the universe. So it turns out that even if you create a computer as big as not just humanly, but universally possible, you're going to run into some fundamental limits. There are problems that we just can't solve with the physical universe itself as our computer. And so here are a number of really interesting papers. This one, for example, Ultimate Physical Limits to Computation, discusses this problem, that the universe only has space for a computer that can solve problems so quickly. And this again comes back to why algorithms are interesting, because not only are our current computers limited, the possible computer that any future human or galactic civilization could build is fundamentally limited by physics. And this is one of the things that I find super cool about this area, is the deep ties to infinity, to philosophy, and then back to computing and mathematics. So compilers, to get around this problem of trying to fit in infinite bits, use a standard called the IEEE 754 float specification. Now this is an awful name, and it's also an unpleasant specification, and so I'm hopefully going to leave that to Dr. John Jong to teach you in a later lecture in class, actually how this representation works. So we're finite, but how finite are we? Does this actually make a practical difference on our computer? It turns out it really does. If you do your arithmetic on the computer using floats, you're quite likely to run into problems even when just doing ordinary calculations. When you're using ordinary mathematical functions like square root, you're going to run into problems, and we'll see a couple of demos from that. So you could use float and run into problems quickly, use double and run into problems a little less quickly, or you could even use long doubles, which are a version of doubles with even more precision, but you'll still eventually run into problems. However, for this class, we'll mostly use doubles, and we'll be fine most of the time. There'll be some special cases that we'll get to where you'll actually need to deal with the fact that the precision is limited. So at this point, is there anyone studying mathematics in this room? Yeah, there are a couple of people, so I'm going to beg your forgiveness for my abuse of mathematical notation and mathematical accuracy in favor of some learning. So this is a representation of, let's say, the integers, and this Z number typically means integers, and we're going to say that these are all 32-bit integers where each of the bits can be either a 1 or a 0. And so we have the number 1 that's in this set and the number 2 that's in this set. So someone from the audience, what is 1 in the integers divided by 2 in the integers? Now I know this is terrible abuse of mathematical notation, but just bear with me. Yeah, what was your name? Yuki? Yuki? 1 over 2? Yeah. What do I get? 0.5. 0.5? Someone else? I've forgotten your name already. Remind me. Olivia. 0? Okay. Any other answers? Okay, Olivia, why do you say 0?
Because it's all in integers, so 1 over 2 would give you 0.
Because 0.5 is not an integer, is it? So this is kind of a weird question I'm asking. What if you take an integer and divide it by another integer and you get a result that's not in the integers? That seems like a bad question. It seems like the integers actually don't have a representation for that, and maybe division doesn't actually exist in the integers in a meaningful sense. For those of you who study group theory, or I'm not sure what the subject is called now, group theory and linear algebra used to be it back when I took it, you'll actually try and understand this problem from a more mathematical perspective, but we're computer scientists. So in this class, we don't actually care about the real answer. We're just going to have to make a decision for what the computer should do. And Olivia's actually right that this is a bad question, but the computer makes a choice, or at least the C compiler does, and says that the answer to 1 over 2 is 0. In fact, what it's going to do is it'll just cut off everything after the decimal place and give you the number out the front. So if I do 3 divided by 2, and they're both integers, what am I going to get? 1, because it would be 1.5. The compiler knows this, but it throws out everything after the decimal place because the answer still has to be an integer, but there's no such integer, so it just throws everything out. Now, this is another common trap that you could run into. So there would be 5 possible ways that we could have solved this. We could have declared that certain equations don't have solutions and just get an error. There are some programming languages that do this. We could force the answer into the real numbers and just say 1 divided by 2, they're obviously asking about the reals. This is what Python typically does. We could leave the answer as a fraction and represent that somehow. We could give both the quotient and the remainder. Or we could give just the quotient, which is what C does. And remember, the modulo operator is the way to separate out the remainder, and so the division operator is going to be the way to get the quotient when you're dealing with integers. So what about this question? Again, terrible abuse of mathematical language. Let's do 1 in the integers divided by 2.5 in the, let's make them floating point numbers. So this is not quite the reals because of the problem we've discussed before, but we at least have some floating points. What do you think? So first question, is this a well-defined question? Hands up for this is well-defined. Hands on heads for this is poorly defined. So I have 1 hand for well-defined, and I think, 2 hands for well-defined, and a bunch on heads. This is a pretty poorly defined question again. You can't like mix and match numbers from different groups or different fields. So bad question, but what are the different options for the compiler to do? Let's get some answers out there. Michael.
Yep. Basically make everything, or make the calculation assume, I guess, the most inclusive sets of floats.
Yeah, so we could do like the Python thing, which it would typically be just, okay, they obviously meant that 1 is a float, we should do that. What are some other options? I didn't hear who that was. Only give the quotient? We just talked about this on the last slide. I need my options back. Come on. Yeah. Give an error. Or there was another one on the previous slide. Okay, Eugene. Leave it as a fraction. Yeah, so I've got the same thing as before. What does C do? These are 3 of the good possible solutions. So declare it doesn't make sense and crash. Approximate the real by an integer, or replace the integer with a floating point number that is mostly equivalent. Now we know that deep down in our hearts, the integers, the reals, and the floats are all pretty different things, But we're programmers, we don't care about any of that. So we are going to do number 3 and replace the integer with an equivalent real number in the floats. So it's a trap. Our C compiler is again behaving in ways that aren't necessarily intuitive. And part of what you'll have to do in this course is just get used to the rules and the quirks of the C language and work around them. So we have a couple of demos. We've already seen overflow.c. Let's take a look at rounding.c. And this might finish off the class. Let's see how we go. So again, I'm going to give you a few seconds to look at this code, discuss it with your neighbor, and figure out what's going to be the output of the code, the usual game we play. Notice that my compiler, my shell, when I press tab, tries to finish words for me. So if I type in, this is the reason why I'm so fast. This is just a helpful shell tip. I press tab. There's only one file that starts with rounding.c, with R, and so it fills that out with rounding.c. Now this is a trap. If I type, I want to make an output file called rounding, so I type R, and I'm used to pressing tab a lot, so I press tab again. What's my problem? I'm going to override it. So you have to be really, really careful with this kind of thing because you can put yourself in some pretty serious trouble and lose a lot of work. So I'm going to be clever. I'll remove the .c. I'll compile it, and let's run the program. And here we see the effects of floating point rounding. So even if you thought that you did the mathematics correctly, the compiler, because it's limited by the number of space available to represent the numbers after the decimal places, is going to give you these weird results. And they're not actually defined in a very clear way exactly what's going to happen. And so it is not our expectation that in the course you'll be able to figure out what this kind of C program would output. You should just know about the limitations of these types. And we have one other demo. Let's see what this one was. I've actually forgotten what this demo was, so we will see. This is another one of the same sort of thing, where the order in which you do operations actually makes a difference. So let's run it. And I encourage you to spend a little more time with this particular demo on your own. I'm not going to step through it step by step. So let's, and I'm going to use my type the letter A and use my tab completion again. So I hit tab, fills that out for me. I'm going to type in that and hit tab again and be very careful to remove the .c. And now I get this strange result again that one wouldn't expect if we had infinite precision. So what are some ways around our overflow problem and around our precision problem? Well, for our precision problem, one way that we can get around it is by using larger types. So instead of using float, we can use double. If we're having a problem with double, we can use long double. Or we can do like the thing that we talked about before, where we add more and more clocks, which gives us more and more bits. And we can write a program which allows us to add as many bits as are available on the computer. That kind of program is not available by default in C. You'd have to use a special library for it. But for the most part, unless you're doing something really, really specialized, you're not going to need more decimal places than a long double. Now, there are places in like simulation or in some of physics or in some other very niche applications where you would want to do this, but well outside the scope of the class. However, our other issue is a little more serious. And in fact, it's a big problem for C in general, this overflow and underflow problem. In particular, in C, if you allow a number to overflow, we get what's called undefined behavior. Now, undefined behavior is more than just saying that the number will wrap around because we know how the numbers work. Undefined behavior is something much more subtle and also much, much more dangerous. Undefined behavior essentially says, compiler writer, this is a problem with the C language, or this is something that we are going to leave up to you to figure out how to handle. Because if we were to tell you how to handle it, it would have a big impact not only on the language itself, but on the actual design of the machine you're running on, because this gets really down into the heart of how bits are stored inside the computer. So, because we don't want to have to deal with every possible way that a computer could be built, compiler writer, if you run into this problem where you get a number that is larger than the largest number that you should be able to have, you can do anything. And when I say anything, I really mean anything. The program's allowed to crash. It's allowed to give you another random number back. It's allowed to print Tetris to the screen. What it means is it's really not part of the C specification what happens next. Now, you can make an informed guess about what the compiler authors are going to do. They're typically not mean people, well, with some exception. The compiler is typically going to behave in one of the ways that we saw and give you the outputs that we saw when we ran the overflow problem, but it doesn't have to. And this problem gets worse because most of the common ways that even that you might see in some of the demo programs written for this course, the ways that overflow is checked for inadvertently rely on the compiler playing nice and giving us well-defined answers instead of undefined behavior. So the checks rely on the compiler being nice and doing this kind of overlap thing. So we really have a problem with the language. So what do we do? Well, one thing we could do is the compiler authors could tell us in advance, and we could know our compiler really well. Or the other thing we could do is we could change the language specification and add some intelligence that is standardized across all the compilers. And as all of you know by now, I'm really, really excited. This is deep in my heart for C 2023. And in C 2023, this is exactly what we've done. We have added some new ways to do arithmetic. So rather than using the plus sign, the minus sign, the divided sign, and the multiplication sign, we have these special and very annoying functions that we can use instead of doing addition or subtraction. And so if you'll see, there is built-in add overflow. And this will give you a well-defined output if the number is going to overflow. Now, I'll upload some demo programs to show you how to use these well outside the class material, but I thought it would be exciting for you to see that, the C programming language is evolving, it is changing. One kind of just subtle point before we finish off for the day. These functions have actually been around in both Clang and GCC for quite some time. The big change that's happening in 2023 is they're being made part of the C standard language. So any compiler that claims to be implementing C correctly must do these things. So we're getting around this problem once and for all. If you want to make me happy, I'd love to see you try and use some of these functions in your programs, but you don't have to. And with that, let's finish for the day. Thank you very much. I will see you all tomorrow at a different time to usual, or different time to today. Same time as on the schedule. Thanks very much, everyone. And thanks for the claps.